Welcome back to Chem Exam Explained, where the aim is chemistry clarity exam mastery. In today's video, we will be looking at Cape Chemistry Unit 1, 2021, Module 2, Kinetics and Equilibria. Let's go. 2A. Table 1 below shows the initial rate of the reaction between substance Q and substance R, measured in a series of experiments, with the following rate equation being deduced. So the rate equation is rate is equal to the rate constant K times the initial concentration of Q times the initial concentration of R squared. So this is our rate equation. We are going to be using the rate equation to answer part 1, using the data from experiment 1. So here we have experiment 1. Calculate a value for the rate constant K and its unit. So right away, we can look at the equation and we're going to make K the subject of the formula. That's the proportionality constant or the rate constant. So K is equal to rate divided by the initial concentration of Q times the initial concentration of R squared. Looking at experiment 1, we can plug in the information given. So the initial rate given in experiment 1 is 1.2 times 10 to the minus 4. The initial concentration of Q is 0.02, and the initial concentration of R is 0.02. Of course, that will be squared. That works out to be 1.2 times 10 to the minus 4 over 8 times 10 to the minus 6. So this is our value, and this value, when you divide the 1.2 times 10 to the minus 4 by 8 times 10 to the minus 6, you get K equal 15. So all that's left now is to work out the unit. So if you look at the formula, K is equal to rate over concentration times concentration times concentration. So it is moles per dm cube per second divided by moles per dm cube times moles per dm cube times moles per dm cube. And we simply cancel out one of the moles per dm cube because we are simplifying the units. So what's left is per second over mole squared dm minus 6. So what we want now is to bring up everything into one level. So we have dm to the minus 6, which once you bring it up, it becomes dm6. Then mole squared becomes moles per squared. And of course, we have per second. And so our unit is dm6 per mole squared per second. And of course, this is the unit for third order. And as you look at the rate equation here, you could see that Q is to the first order and R is to the second order. So the overall order is third order. Let's move on to part 2. Complete table 1 above by inserting the missing initial concentration of Q, the initial concentration of R, and the initial rate for the reaction between Q and R. Let's go back to table 1, where you'll see that we have some blank spaces to fill in. So if we are required to find the initial concentration of Q, from the rate equation, we can make Q the subject of the formula. And to find for R, we'll do the same thing, make R the subject of the formula. Now, let's look at Q, then R, and then we can find the initial rates for experiments 2 and 3. So we are starting now with finding Q. Now to find Q, which is the initial concentration of Q, we're going to look at our experiment 3. So experiment 3 will help us to find Q. So here we go with experiment 3 to find Q. We start with the rate equation, rate equal K times the initial conc of Q times the initial conc of R squared. And we simply make Q the subject of the formula. And then we plug in the information that we have from experiment 3. So what do we have from experiment 3? we have the initial rate. So we have 2.4 times 10 to the minus 4. We plug that there. We have K, which was calculated here. So we put R divided by K times R squared. So this R is the initial rate divided by the rate constant K times the initial concentration of R squared. So we now have 2.4 times 10 to the minus 4. You can find that here, divided by the calculated value for K times 0.04 squared. And that works out to be Q equals 0.01. And we plug in that information here. We'll do the same thing to find for R. So to find for R, we're going to use experiment 5. Now, what do we have? We have the initial rate for experiment 5, and we have the value for the initial concentration of Q. So we need to find R. How do we find that? Here we look at experiment 5, so we're going to use this to find R. So looking at the equation again, rate equal K times Q times R squared. This is the rate, the initial rate, and this R is the initial concentration. So we're going to make this the subject of the formula. So then R is equal to the square root of the, so R is equal to the square root of the initial rate divided by the rate constant K times the initial concentration of Q. And we simply plug those values in. So R is equal to the square root of the initial rate, which is 7.2 times 10 to the minus 4. You can see it here. And of course, divided by 15 times 0.04. So this divided by 15, which is K that we calculated here, times the initial conc of Q, 0.04. And we find the square root of that. And our value for R is equal to 0.035. And we put the value here. Now to find the initial rate for experiment 2, we're going to use the same equation from experiment 2 here, and we're going to find the initial rate. So what do we have? We have the initial conc of Q, we have the initial conc of R, which must be squared. And so the initial rate is equal to 15 for the rate constant times 0.04 times 0.04 squared. And that works out to be 9.6 times 10 to the minus 4. And we have our value there. To find the initial rate for experiment 4, we do the same thing. And so we look at experiment 4 here to find the rate. So what do we have? We have K that we calculated in part 1 times the initial conc of Q, which is 0.06, which you will find right here, 0.06 times 0.03 squared. And the initial rate works out to be 8.1 times 10 to the minus 4. 2A part 3. The order of the reaction with respect to R is 2. State the meaning of the term order of reaction with respect to R. So the order of the reaction with respect to R is the power to which the concentration of R is raised. This means that as the concentration of R increases, the rate increases exponentially. So this is saying that the concentration of R is second order. 2A part 4. Deduce the overall order of the reaction between Q and R. So if you look at the rate equation, you'll see that the order with respect to Q is first order, so we put 1. The order with respect to R is second order, so we put 2, and you sum the orders to get third order. 2B. A fixed mass of marble lumps is reacted with dilute hydrochloric acid at a constant temperature. Outline why the rate of the reaction would increase if the lumps of marble are reduced in size. So right away, we can now compare lumps with respect to powder. And we know that powder would have a higher surface area. So the powder would increase the surface area. So increased surface area would cause more effective collision to occur. This will increase the rate of the reaction. That is, more marble would be available to react with the hydrochloric acid. 2C, when a 0.218 mole sample of hydrogen iodide was heated in a flask of volume VDM cube, the following equilibrium was established at 700 Kelvin. So this is our equation. We have hydrogen iodide decomposing to form H2 gas and iodine gas. And in a closed system, equilibrium would be established. So the equilibrium mixture was found to contain 0.023 mole of hydrogen. The first part of the question requires us to calculate the number of moles of iodine and the number of moles of hydrogen iodide in the equilibrium mixture. So the first thing we're going to do is to establish our ICE table. So ICE for the initial concentration, C is for the change that will occur, and E is what is taking place at equilibrium. The first thing I want to say is that what we have here is 0.18 moles. However, it is in a particular volume in the flask, which is your closed system. So having 0.018, we are going to treat it like it is concentration. So the conc of HI is equal to 0.218 moles divided by volume in dm cube. So bear this in mind when we are working with our moles here. It is really concentration, but because we don't have a set volume, we're just going to treat the mole as if it is concentration. But remember, we are working with concentration. So this is the initial concentration. Remember, initially, no reaction is taking place, so you don't produce any H2 or I2. But once the reaction starts, we will have a change. What is that change? We can find the change by knowing the volume of H2 gas produced at equilibrium. This is key. So at equilibrium, we have 0.023 moles per dm cube of H2. Now, how do we find the change? If you see that we produce 0.023 moles per dm cube of H2 at equilibrium, it means that that was added here. Since the mole ratio is 1 to 1, it was also added here. So we know the initial conc of I2 is 0, but the change when the HI starts to decompose, it produces 0.023 moles per dm cube of I2. So at equilibrium, we also have 0.023 moles per dm cube of I2. So we know the moles of iodine to be 0.023. We just calculated that. And we know the moles given in the question of hydrogen at equilibrium. So with that, we can now find the moles of HI at equilibrium. Now, all we do, looking at the stoichiometric ratio, the change would be, because it is on the reactant side, we're going to be subtracting the 0.023 times 2, because the mole ratio is 2. So if you multiply 2 times 0.023, we are going to subtract that from the initial concentration to find the concentration of HI at equilibrium. And that works out to be 0.172. So now we have all the values for HI, H2, and I2 at equilibrium. We can now go on and do further calculation. Now notice that the K given here is 700 Kelvin. We don't need to do anything with this value. It is just telling us that this reaction takes place at this temperature. So right here, we have now the number of moles of hydrogen halide to be 0.172. 2C part 2. Write an expression for Kc for the equilibrium. Now, let's rewrite the equation that we had. We had 2HI reacting to produce H2 plus I2. So to write the constant Kc, which is the equilibrium constant for concentration, it is the product of the products. So the first product is the multiplication. So it is a conc of H2 times the conc of I2 divided by the product of the reactants raised to their coefficient. So it will be the product of the products raised to their coefficients. In this case, it is 1, so we don't show it, divided by the product of the reactants, which is HI raised to the power of 2. And that will give us the equilibrium expression. Part 3, calculate the value of Kc at 700 Kelvin. You would recall that we calculated the values for H2 at equilibrium to be 0.023 moles per dm cube, and the same thing for I2. And the value for HI was calculated to be 0.172 moles per dm cube. So all we'll do now is plug those values into the expression and we'll get our answer. In this case, Kc equal 1.79 times 10 to the minus 2 once you plug the values in and calculate it. Please remember again that these values are not moles because they are divided by a certain volume. Concentration is moles divided by volume, which gives us a unit of moles per dm cube. Part 4, calculate the value of Kc at 700 Kelvin. Again, notice they are not asking for a different temperature. They're asking for the temperature at which this experiment was carried out. So let's calculate the value for Kc at 700 Kelvin for the equilibrium of the reaction. So this is the reaction, but notice that now this is the reverse of what we had before. So this is the decomposition, but the reverse is H2 and I2 reacting to form HI. So notice that we're not looking at the same equation before. This is now the reverse. So H2 and I2 becomes the reactant while HI is now the product. So the expression would be the product of the products raised to their coefficient, that is HI squared, divided by the product, the multiplication of the reactants raised to their coefficient. And of course, we plug in the same values and calculate it, and we get now 55.96. Now, you're probably asking, where's my unit? If you realize that this concentration is squared, so it's moles per dm cube times moles per dm cube divided by moles per dm cube times moles per dm cube. All our units are cancelled, so this value is dimensionless. 2D. Buffer solutions are necessary in a wide range of applications, ranging from biological systems to industrial processes. Part 1. State the meaning of the term buffer solution. Now, a buffer solution is a solution of a conjugate acid-base pair that resists changes in pH when small amounts of acids or bases are added. Part 2. Identify a reagent which could be added to a solution of ammonia in order to form a buffer solution. What I want you guys to realize is that we have two types of buffer. You have an acid buffer and a base buffer. So if you have an acid buffer, you need two things. You need an acid, for example, CH3COOH, and you need the conjugate base, which is CH3COO minus. Now, so you're not confused, I could put Na plus here. But this is the acid and this is the conjugate base. This is an acid buffer. A base buffer consists of a base and a conjugate acid. In this case, NH3 would be the base, and the conjugate acid would be NH4 plus. Again, so you're not confused, I could put Cl minus. So here we have acid, and this is your conjugate base. This is an acid buffer. While here we have a base and now a conjugate acid. And this now is a base buffer. So to identify the reagent, we must write the conjugate acid of the base. In this case, it is NH4Cl. Part 3, consider the following equation, which represents a buffer solution consisting of a weak acid and its conjugate base in water. So let's go again. Let me just remind you that notice that this is a weak acid. So a buffer solution is normally a weak acid and its conjugate base, or a weak base and its conjugate acid. Now, when you add acid or base to a buffer, something is going to happen. Now, let's look at the equation in part 3. We have HA, which represents an acid. And, of course, A minus represents the conjugate base. So this is the acid, and this is the conjugate base. But when you react this acid with water, it means then that if HA is the acid, then water must be the base. And if water is the base, then it forms a conjugate acid here. The hydroxonium ion, H3O plus, is now the conjugate acid. So you notice that for this reaction, we have a conjugate acid-base pair. So let's explain the effect of the buffer solution if the concentration of H plus ions and hydroxide ions are increased separately. If you increase H plus, which is suggesting that you are increasing the acid concentration, something must react to counter it. So if you're adding H plus, which is an acid, then the conjugate base must counteract it by reacting with it, decreasing the concentration of H plus that was added, hence maintaining a constant pH. Remember, a buffer solution resists changes in pH when small amounts of acids or bases are added. If you increase OH concentration, then what is going to counteract that increase in base? The acid will counteract it. So when you add OH minus, the acid will counteract it to decrease the concentration of OH minus. Part 4. Explain how the molecular structure of amino acid relates to their function as buffers in human blood. So right away, we want to look at the structure of amino acid. Here we have NH2, which is an amine, which we know is a base because of the lone pair on the nitrogen. This is a simple amino acid. Given that we only have CH2 here in the middle, you could have several chains of hydrocarbon in the middle, which will give you a different amino acid. But this is a simple amino acid. So we have an amine part, which is a base, and we have the carboxylic acid part, which is an acid. So having an acid and a base in this structure, which is amino acid, amine, amino, carboxylic acid, amino acid, the acid will donate a proton to the base, and the base will accept the proton because it has a lone pair on the nitrogen. So what do we form? We form the conjugate acid from the base because you now have one extra proton. And from the acid, you form the conjugate base because you have one less proton. So this structure now that we just formed is Zwitter ion. So this is how our blood works to maintain a constant pH by using now a buffer system in the form of Zwitter ion. So when we have an increase in acid concentration in our bodies, which part will counteract the increase in acid? Remember now that this part is basic. So this part was our conjugate base. And this part was our conjugate acid. So increasing H+, what will counteract it? Is it the acid or the base? So we'll see that the base will counteract it by reacting with it to form back an acid that was already present in our original structure, hence maintaining a constant pH. All right? This one, we are increasing the concentration of OH minus ions. So the conjugate acid must counteract the base. And how? It will give up a proton to form water. So once H+ was lost from the conjugate acid, it is added to the OH minus to form water. And we now form back our amine that was already present. So zwitterion works to maintain a constant pH in our bodies. Hence, it functions as buffers in blood. 2E. In a laboratory exercise, students are asked to determine the pH of a buffer made by the addition of measured quantities of ethanoic acid and sodium ethanoate. So here we have our acid and we have the conjugate base. So this is a weak acid and its conjugate base. So this is a acid buffer. Part 1. Identify 2 relevant pieces of apparatus and or materials that may have been used by the students to carry out the experiment. Well, if we are trying to determine the pH, we definitely need a pH meter. You also need a container to put our buffer solution, as well as distilled water. But the main 2 relevant pieces of apparatus would be the pH meter and the beaker. The water would be like a reagent, but it did not ask for a reagent, so we can ignore the water and focus on the 2 pieces of apparatus. Well, it did say or materials that may have been used. So you could use the distilled water if you don't remember the 2 pieces of apparatus. E, part 2. Identify 2 relevant experimental steps that may have been taken by the students to determine the pH of the buffer. Well, 1, prepare the buffer solutions with desired concentrations. And 2, calibrate the pH meter using known pH of standard buffer solutions. So you have to prepare your buffer solution and you want to find the pH. You need the use of the pH meter. One of the ways we want to ensure that it is accurate is to ensure that it is calibrated. This is the end of Module 2, 2022. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.